Okay, folks, just a short video this time to prepare you for tomorrow's lab. We're not quite done with material in Chapter 10. I'd like to circle back to the last section about gyroscopes because I think it's a really interesting topic. But in the interest of moving forward and looking at tomorrow's lab, we only have a little bit to say about the first half of Chapter 11. So, Chapter 11 starts off defining what it means for a rigid, extended body to be in equilibrium. And we had one condition for equilibrium. The sum of the forces on the object must be 0. We were solving equilibrium problems back in Chapter 5 before we really knew to call them equilibrium problems, so that's exciting. But now that we've defined rotational force on Tuesday, we can also say that in order for an object to be in equilibrium, not only must the net force be 0, but the net torque on the object must be 0 as well. That's basically all we need to know. Essentially, this is section 11.1. Section 11.2 talks about center of gravity and stable or unstable equilibrium, and we'll kind of circle back to that as we finish Chapter 11. For tomorrow's lab, what we really need is section 11.3, solving rigid body equilibrium problems. During the lab tomorrow, you're going to have a setup something like this. You'll have a support, a fulcrum, and a meter stick balanced on that fulcrum. You'll have some mass hung at different places on the meter stick. And then this end will be supported, a stack of something here, on our digital balance scales. So we've got it level and at rest. It's not rotating and it's not accelerating linearly, which means the system that you're talking about is in equilibrium. So we'd like to make sure that we have a handle on how we can use the conditions of equilibrium to solve the problem, to figure something out. Okay. Now, I think the easiest way to do that is to look at an example. And I'd like to work through example 11.3. What we've got, the example talks about Sir Lancelot climbing a ladder to get into a castle. I don't know how important the context is, but we've got a 5-meter ladder. And it's leaning against a castle wall. This contact between the ladder and the wall is frictionless. The ladder has a weight of 180 newtons. The angle that the ladder makes with the horizontal is 53.1 degrees. And our intrepid Sir Lancelot has stopped a third of the way up the ladder. That's Lancelot, I guess. Lancelot weighs 800 newtons, by the way. and he has stopped a third of the way up. I'll just call this L over 3 for now. We are supposed to find the normal and frictional forces at the base of the ladder here on the ground. A, find the normal force and the frictional force at the base. B, find the minimum coefficient of friction needed to prevent slipping. Okay. Minimum mu. Static because it's not moving. Find the magnitude and direction of the contact force on the base of the ladder. Okay. So if, let's say in part A at least, that this is in equilibrium, there are two conditions that we know that have to be true. We know that the sum of the forces has to be 0, and we know that the sum of the torques has to be 0. Now, if we've got a torque, that means we're rotating about somewhere. We can choose any point we like to rotate around, because it's not rotating about any axis. It's not rotating at all. So if we pick, I don't know, if we pick at the point down here at the base of the ladder, we can talk about rotation about that axis just as well as we could talk about rotation around this axis. They all have to sum to 0 torque because there isn't rotation about any axis. So we can feel free to pick an axis of rotation to talk about that makes our math convenient. Okay, first, let's talk about which object we're interested in. And it's a little bit confusing because there's Lancelot and a ladder, but really what we're interested in is the ladder. And let's redraw the ladder itself. And then let's sort of do an extended free body diagram. We're not really talking about the ladder at its center of mass anymore like we used to. We're talking about the ladder and all the forces that are acting on the ladder, including the locations at which they act. Okay. So if we've got the, let's see, we've got the weight of the ladder. W ladder. What else have we got? Well, part A asked us for the normal force and the friction force at the base. So I guess we know that there are those two things. Here's normal force, perpendicular to the ground, and the friction force. And I guess we have a choice whether it's to the left or the right. And then the question is to think about if the ladder were going to slip, which way would it slip? If it slid down the wall, the back end would be sliding away towards the left. Friction wants to oppose that, so friction needs to point to the right. Okay. The other force acting on the ladder is the weight of Lancelot. And that acts a third of the way up. Now, where does the weight of the ladder act? The ladder is uniform. So the center of mass of the ladder is at its geometrical center. And that's where the weight of the ladder acts. Okay. Lancelot is only a third of the way up, so his weight is going to act on the ladder this way. I can't use L because I used it for the ladder, so I'll just call it the weight of the knight, I guess. Okay. Now, just from a force standpoint, something about this diagram doesn't seem right to me. We've got up forces and down forces, and those can cancel, I suppose. That makes sense. But this is a force to the right. There needs to be at least one other force to the left. Otherwise, we aren't meeting this equilibrium condition. Can you see where the left-going force comes from? The answer is the ground isn't the only surface interacting with the ladder. There's also the castle wall. There's no friction, but there might still be a normal force. From the wall. Okay. Last thing I want to include here is the angle, 53.1 degrees. Okay, and now we can start writing some things down. Now that we've got this free extended body diagram, we can say that the sum of the forces in the x direction needs to be 0, which means the force of static friction has to add to the force of the normal force from the wall. They're opposite directions, so one of them needs to be negative, so we can solve that way. And the other thing we know is that the normal force, let me start with the force in the y direction needs to be 0. So that means the normal force from the ground needs to be equal to the weight of the knight plus the weight of the ladder. Okay. Now, we know some of this already. I think we have enough to solve for the normal force, which was the first thing we wanted. We know the weight of the knight, of Sir Lancelot. We know the weight of the ladder. That's just 800 plus 180 newtons equals 980 newtons. Okay, fantastic. How are we going to figure these out? How do we know? Because we don't know what the coefficient of friction is. Plus, we're not even sure if this is in, the threshold case. And the answer is we need to use the other equilibrium condition. Okay, so we know that the sum of the torque needs to be equal to 0. About which axis? Now, we can pick any axis we like. And I'm thinking that if we pick this axis down here, that we're talking about the ladder, hypothetically, rotating around the base of it. So in other words, we're fixing down here and allowing it to rotate this way. Now, it's not actually doing that, but this is the math that we're going to write. Okay, so we've got 1, 2, 3, 4, 5 forces that are potentially exerting torque. Let's get a term for each one in the sum of the torques needs to be 0. Okay. So here we're going to use our formula for torque in terms of force that we developed on Tuesday. But first, let's write, we got the torque from the normal force on the ground plus the torque from the force of static friction plus the torque from the weight of the knight plus the torque from the weight of the ladder plus the torque from the normal force from the wall equals 0. Okay. This is the distance away from the axis, the position vector, right? From the axis of rotation to the point of action of the force in question. Plus our friction cross the force of friction plus our weight of the knight cross F weight of the knight plus our weight of the ladder cross F weight of the ladder plus our normal force from the wall cross F normal force from the wall. And again, we're just using the definition we developed on Tuesday, R cross F equals torque. For each of the 5 forces, it is possibly exerting a torque, and we're just making room for each one to exert its own torque. All right, so let's examine. The normal force acts at the point we chose for the axis of rotation. So what's that position vector? Like, what is the position vector from the axis of rotation to the point of action? It's 0. And the same thing is going to happen with the force of friction. Friction acts at the point we chose as the axis of rotation. So the vector that points from the axis of rotation to the point of action of friction is 0. It's the same point. And as you're solving equilibrium problems, choosing a point as the axis of rotation at which one or more of your forces acts helps to simplify the torque equation, because any forces that act at the axis you pick exert 0 torque there. Okay, so we keep going. Let's see, so this is the position from the axis of rotation to the point of action of the weight of the knight. Well, that's a third of the way up the ladder. So I'm saying the magnitude of that position vector is a third the length of the ladder. The weight of the knight is 800 newtons. And then, so let's see, the cross product is magnitude of the first thing, magnitude of the second thing, sine of the angle between them. And the angle between a vector along the ladder out the way, the angle between that direction and the down direction is that angle, right? It's the 53.1 plus 90. 90 plus 53.1. Now, this force, if it were to cause the ladder to rotate. Again, let's fix the point at the end and push down like the weight of the knight would do. That force, if it caused the ladder to rotate, would tend to make it rotate clockwise. Okay. And we said that clockwise rotations were negative and counterclockwise rotations were in the positive direction, because that's how we define positive angles. The vectorness of these torques. Now, all of the problem is happening in the plane of the paper. We ask for the angular acceleration vector. It points perpendicular to the paper. One direction perpendicular to the paper would be positive. The other way would be negative. Since this is causing clockwise rotation, let's include a minus sign. Okay, let's keep going. The weight of the ladder is, again, okay, so we got halfway up the thing, magnitude of that position vector from the axis of rotation to the point of action of the force, the weight of the ladder, the sine of the angle, and it's the same angle, which is 143.1. And again, this force, if it were to cause the ladder to rotate, would cause it to rotate clockwise. Let's include a minus sign. Okay. Last term. I'm running out of space, so I'm going to move down a line here. The distance along the ladder to the point of action of the normal force from the wall, that's the entire 5 meters. The normal force from the wall, we don't know what it is, so I'm just going to leave it as normal force from the wall. Magnitude, sine of the angle between. Now, the angle between the vector from the axis of rotation to the point of action, that's this direction. But we want to talk about the angle between that and the normal force from the wall, which means we have to take it from here and spin all the way around so that we point this way. We're talking about this angle, which is 180 minus 53.1. 180 minus 53.1. All right, now is this a clockwise or a counterclockwise torque? If we fixed the axis of rotation here, this force, if it were to cause the ladder to rotate, would cause it to rotate counterclockwise. So let's keep this term positive. And that all adds together to 0. Okay. Let me scoot down to a new page here. And let me grab a calculator. All right, so let's clean up our equation here a little bit. The normal force from the wall, that's our unknown. These two terms are negative, so let's move them to the other side where the 0 is so that they can be positive. And then we can just multiply and then add the terms together. Divide by 5 and the sign of this guy. And let's see what we get. Give me a couple seconds to do the math. Let me write the expression here. We've got the normal 5 meters over 3, 800 newtons. Sine of 143.1 plus 5 over 2 meters, 180 newtons, sine 143.1. All divided by 5, divided by the sine of 180 minus 53.1. All right, and if we do that math, we end up saying that the normal force from the wall is one second. Two 67.8 newtons. Okay, now how does that help us? That's not what we wanted. The problem asked for the friction force at the base of the ladder, but one of our force equilibrium equations related the normal force from the wall to the friction force. So we just found it. The frictional force at the base of the ladder is 267.8 newtons to the right in our diagram. Okay. Next step was to find the minimum coefficient of friction that would get the job done and keep the ladder from slipping. Well, that part asks quite a bit less of us, actually. Now that we know what the friction force needs to be in order to keep the ladder from slipping, we can relate that to the normal force at the same point and evaluate the coefficient that way. I mean, remember, the force of static friction in the limiting case is equal to mu times the normal force. The ladder isn't in equilibrium unless the force of static friction can be this big, right? So the least we can allow the coefficient to be is such that given the normal force, the force of static friction is equal to this. It could be bigger than that. In other words, the coefficient could be larger than this. Friction, the needs from friction will only be this big in order to keep the ladder stable. But it can't be any smaller. If the effective force of friction is less than this, then it will slide. Okay, so we're just talking about mu s equals force of friction static over normal. 267.8 over the normal force we said was 980. equals 0.27. Okay, so far so good. Only one piece left. They wanted to know the contact force on the base. Okay, well, we know what the forces are on the base of the ladder. It's the normal force and the friction force, and we know what both of those things are. So we just need to find the magnitude and direction. Okay, fine. The normal force is 980 newtons. The friction force is 267.8 newtons. And if we want the overall magnitude, F, I'll put contact, F contact, is just the Pythagorean theorem. So 1,015.9 newtons, and if we need the direction, it's arctangent of 980 over 267.8. .7 degrees. Okay, so most of this example, well, the other two parts of this example, B and C, are things we've seen before. The big news here from this example is the method of equilibrium, and I want to look back at it one more time. We drew a sketch with some information in it, and then the next step was to redraw the rigid body of interest. What is it that we're saying is in equilibrium? Say yes, Lancelot is in equilibrium, but the interesting thing here is the ladder. And one of the reasons we know that is that the questions ask about the forces acting on the ladder, not on Lancelot. So we redraw the ladder, and then we draw all the forces that are acting on the ladder, including the locations at which they act along. Once we've gotten this sort of extended body diagram, we go through the equilibrium conditions. Some of the forces, some of the forces, some of the torques. And the nice thing about torque in all of the problems we're going to talk about, the problem sketch, the extended body diagram, is a two-dimensional thing, which means the rotation we're talking about is only ever clockwise or counterclockwise or clockwise. So we can handle the vector nature of torque by including minus signs or plus signs, depending on whether we're going counterclockwise or clockwise. The magnitudes we can handle with the cross product, magnitude, sine of the angle. And the directions we handle with the minus signs according to which way we would be rotating. Okay. That's essentially all we've got to say. Let's take another look really quickly at the setup in tomorrow's lab. Just to get the setup done. What you're going to have, again, is a meter stick, a loaded meter stick, with some mass hanging off of it at a couple different places, resting on a digital balance. And it's going to be at rest, and it's not going to be rotating, and it's not going to be accelerating. So that means it's in equilibrium, and that means we're going to know that the sum of the forces and the sum of the forces in the x and the y and the sum of the torques is 0. This fulcrum supporting the end of the meter stick, we're not going to know anything about. I mean, I guess we could find it using the conditions of equilibrium. Let's draw that extended body diagram we're talking about as far as the meter stick goes. All right, so there's a normal force here from the fulcrum. There's the weight of the mass hanging here. Weight 1, let's call it. There's the weight of this mass hanging here, weight 2. There's the normal force from the scale. And there's the weight of the meter stick itself, which we have to be careful to include. Okay. This drawing is the drawing that I recommend, I guess the weight of the stick. The drawing that I recommend that you use for the last couple procedure steps on the lab when we are supposed to evaluate the location of the center of mass of the meter stick itself. I think you're going to need to use the torque equation for equilibrium, and I think that you should pick this as your axis of rotation, because then we won't need to know the force from the fulcrum. It's not something we measure, so if we pick this axis, then the vector from the axis of rotation to the point of action of the fulcrum's force is 0, and so that torque will be 0. So that means we don't need to know it, which is great. Earlier in the lab, it's going to ask you to use this configuration to find the center of mass of the system. Okay, and for that calculation, I recommend a slightly different diagram. Imagine that the meter stick and the masses are all one object, and we're trying to find the center of mass of that object. So we've got the same setup here. We've got the object, the system in question. There's a fulcrum holding up one end with a force acting there, normal force, and there's the scale holding up the other end. The only force that can balance these two, cancel it so that it's in equilibrium, is the weight of the system itself, which we know acts at the center of mass of the system. So this, from one end, doesn't matter which end you pick, from one end where you can talk about the distance of the center of mass of the system away from, if we pick this one again as the axis of rotation so that we don't need to know that force, the distance from the axis of rotation to the center of mass of the system. And these two forces are the forces that we need to talk about in our torque equation. So the weight tends to make us go clockwise. So we'll say negative RCM W system. If the meter stick is level, then this is a horizontal vector and weight is vertical. So then we're talking about the sine of 90 degrees. So we don't need sine of 90 is 1. This force, the force from the scale that we can measure, is the entire distance of the meter stick. Our total, I guess, I guess 1 meter, right? Times the normal force from the scale. Again, the angle is 90 degrees. And those are going to add to 0, and you can solve for we call this the experimental location of the center of mass of the system. Okay, and then we can go back to our assumption that we made about the fact that the meter stick is uniform. Is the center of mass of the meter stick itself actually halfway along its length? Or, since our equilibrium result here maybe gave us a slightly different value for the center of mass of the system, is the center of mass of the meter stick slightly to one side or the other? And can we figure out where? Okay. I think that's all the material I need to cover to prepare you for tomorrow's lab. I am going to post along with this video a handout, a worksheet to practice equilibrium stuff. It'll do after break, we'll talk about it. And since I'm not going to see you this week, I just want to wish you a very happy and healthy spring break. And thanks, everybody, for putting up with my not being there. All right, take care.